In severely arid environments, the creeping herb Boerhavia Diffusa can survive near total desiccation. When exposed to moisture, the withered plant rapidly swells and blooms, regenerating its cellular structure in a matter of hours. Classical Ayurvedic texts observed this resilience and classified the plant as a rasayana, a systemic rejuvenator, historically prescribed to purify the urinary tract and restore fluid balance. Modern clinical data presents a complex profile of this plant. Documented clinical trials and in vivo studies show it improves estimated glomerular filtration rates in kidney disease, inhibits melanoma metastasis by up to 95%, and significantly delays chemically induced seizures. Modern pharmacology inherently distrusts this kind of broad efficacy. When a single botanical source claims to treat the renal, oncological, and neurological systems simultaneously, researchers typically assume the results are either a placebo effect or nonspecific antioxidant noise. The data, however, points to a different reality. The plant's efficacy does not rely on a single, uniform compound acting systemically. It relies on a sophisticated matrix of highly distinct molecules operating independently. Chemical fractionation of the root and leaf extracts isolates three primary phytochemical classes driving these specific mechanisms: rotinoids, alkaloids, and lignans. To evaluate the actual clinical viability of this plant, we have to abandon holistic generalizations. We need to systematically deconstruct its molecular drivers and map them to their exact cellular targets. Starting with the renal system, the clinical baseline is well established. Administering root extracts of Boerhavia Diffusa to patients with chronic kidney disease consistently reduces serum creatinine and improves the estimated glomerular filtration rate. To address severe edema and fluid retention, modern medicine relies heavily on synthetic loop diuretics, such as furosemide. This cross-section of a renal tubule shows how these synthetic agents operate. The drug molecules attach directly to the membrane, physically forcing a high volume of water molecules out of the tubule to reduce fluid retention in the body. The clinical limitation of these synthetic agents is their lack of selectivity. They induce a nonspecific electrolyte dump, dragging potassium ions out of the tubule alongside the water, and triggering severe potassium depletion or hypokalemia. The active rotinoids found in Boerhavia diffusa, specifically boeravinones A through G, offer a different molecular approach. Once docked on the tubule membrane, these boeravinones work as targeted osmoprotectants, successfully increasing fluid output and moving water out. The critical distinction is that the potassium channels remain stable. The potassium ions are secured safely inside the tubule, maintaining the body's electrolyte balance despite the high fluid output. Alongside this osmotic regulation, in vitro assays of the extract demonstrate a 45% reduction in COX-2 expression within inflamed urinary tract cells. This concurrent action means the renal tissue experiences simultaneous fluid regulation and targeted anti-inflammatory relief. By achieving a highly targeted potassium-sparing diuresis, boeravinones provide a molecularly precise alternative to the systemic electrolyte crashing caused by standard synthetic drugs. In oncological models, the data reveals a different specialized action. Prophylactic administration of the extract in murine models inhibited the formation of experimental B16F10 melanoma pulmonary metastases by up to 95%. The specific molecular driver responsible for this anti-metastatic effect is an isolated alkaloid known as punarnavine. To understand this effect, we examine how tumors physically invade tissue. This model illustrates a melanoma cell pressing against a dense extracellular matrix. The cell deploys matrix metalloproteinases, specifically MMP2 and MMP9, which function as enzymatic drill bits, degrading the barrier. Punarnavine actively disrupts this process. The alkaloid molecules locate and bind directly to the active sites of these specific MMP enzymes. Zymogram analysis confirms this binding, neutralizes the gelatinase activity of the MMPs. The physical degradation halts, the extracellular matrix stabilizes, and the cancer cell loses its ability to invade the surrounding tissue. While the physical invasion is blocked, a secondary immunological mechanism occurs. Punarnavine upregulates the production of IL-2, aggressively stimulating natural killer cell activity. Simultaneously, the alkaloid downregulates the host's pro-inflammatory cytokines, driving down levels of IL-1 beta, IL-6, and TNF-alpha. This dual adjustment strips the tumor of the inflammatory microenvironment it requires for angiogenesis and long-term survival. Punarnivine operates as a dual-action barricade. It halts tumor progression at the physical, enzymatic level, while simultaneously weaponizing the host's own cellular immune response. The plant's neurological data centers on its documented efficacy in delaying the onset and reducing the severity of pentylene tetrazole-induced convulsions. Strict fractionation of the extract proves this is not a broad-spectrum sedative effect that depresses the entire central nervous system, but rather a highly targeted intervention at the synapse. Looking closely at a neural synapse, we see the physiological trigger for chemically induced seizures. The calcium ion channels lock in an open position, permitting a massive, unregulated flood of calcium ions across the synaptic gap, causing erratic electrical hyperexcitability. The active anticonvulsant effect is driven by an isolated lignin called liriodendrin. Liriodendrin functions strictly as a potent calcium channel antagonist. The molecules dock precisely onto the open channels, physically obstructing the pathway. This targeted antagonism immediately restricts the flow of calcium ions, pulling the firing rate out of a hyperexcitable state and stabilizing the synapse back into a normal rhythm. By blocking this specific ion pathway, the lignin directly delays the onset of convulsions and reduces their overall severity in animal models. Liriodendrin proves that the extract's neurological efficacy is the result of precise molecular docking and receptor antagonism, disproving the assumption that the plant simply acts as a generalized nervous system depressant. We have now mapped three highly distinct actions: renal diuresis driven by boravinones, immune defense engineered by punarnavine, and neural stabilization governed by liriodendrin. This brings us back to the initial paradox of the ancient Rasayana, a single botanical source used as a systemic panacea. This diagram illustrates that when subjected to strict chemical fractionation, the historical concept of a panacea aligns directly with modern multi-target polypharmacology. Three distinct molecules are acting on three specific biological targets. Because these molecules possess genuine pharmacological potency, they require strict clinical boundary setting. First, clinical data indicates the plant's extracts must be limited or entirely avoided in early pregnancy due to the potential for unintended uterine stimulation. Second, due to its efficacy as a diuretic and vasodilator, the extract should not be used concurrently with hypotensive medications or strong synthetic diuretics, which could trigger dangerous additive physiological effects. By moving past the holistic generalizations of traditional herbalism and mapping exact molecular mechanisms, researchers can extract these specific compounds to develop a new generation of highly targeted, low-toxicity therapeutics.